All right, 5-3 day 2. The topics are still conditional probabilities and independence. So it says on our first example here that the probability that a pitcher in a baseball game throws a perfect inning is 40%, which means they are pitching to the first batter and they get them out, and then they pitch to the second batter and they get them out, and then they pitch to the third batter and they get them out. Okay? They only faced 3 batters, they got all 3 of them out. If we were to assume that each inning is independent, okay, what are the odds the pitcher would throw a perfect game? We are able, as the problem told us, assuming independence, that we could just multiply each inning by the next inning. The quick way to do that would be take 0.4 and raise it to the 9th power, and you'd get 0.000262, which, if you're into interpreting probabilities, which we are, that's low. That would tell you that a perfect game in baseball is quite rare. Okay? Now I want to throw some formulas your way that are really based on what all this is about. I believe in day 1 I gave you a really important one that said the probability of A given B is the probability of both A and B occurring divided by the probability of B. Okay? That's a really, really good one to know. All right? Your book will refer to that as your conditional probability formula. Okay? What's going on here is actually kind of a different form of this formula. If I were to multiply both sides by the probability of B, I would get this. Same formula, just rearranged, okay? So this would be good to get the probability of any problem that says, you know, the first event and the second event. And here it's really 9 events, 1 for each inning, okay? But remember this. It told us in this problem that it was independent, which means the probability of A given B is the same as just the probability of A, right? Your condition wouldn't matter, which is why we could say probability of A times the probability of B. We don't have to pay any attention to the condition. If A and B are independent. Okay? That really, I mean, these two formulas really are the same thing, but the one in red does have the condition that the 2 events are independent. Okay, the one in black you could use all the time because you're factoring in the condition of B. This one's kind of interesting, as it doesn't really get into any calculations, but it illustrates what independence is all about. In the previous problem, it was that an inning, how a pitcher fared one inning, was not related to the next inning. Okay? So this is using that same rule that, hey, if there's a 50% chance that it's going to rain in La Puente, I think that's how you pronounce it. I never took Spanish. Does that mean that, and there's a 50% chance it's going to rain in Hacienda Heights, do we just multiply them and say, hey, there's a 25% chance it's going to rain in both? Well, the answer is no. And here's why. The weather in neighboring cities isn't independent, okay? The fact that they're that close together, if it was likely to rain in one of those cities, it's probably going to rain in the other, or at least there's a really good chance that it will. Independence means that if I told you the weather about one city, you're like, hey, that doesn't tell me anything about the weather in the other, okay? Like if we were comparing 50% chance that it's going to rain in the LA area and a 50% chance that it's going to rain in New York, then yes, I would be okay saying 0.5 times 0.5, 25% chance that it's going to rain in both. Weather in these two cities is independent. Totally across the country as opposed to cities that neighbor each other. Okay? All I want you thinking about there is the idea of independence. If you've got two events and the outcome of one isn't related to the other. And remember in day one we went over how to check that. Okay? If you calculate the event and then you calculate it again with the condition, it should be the same. If they're independent, it will be the same. All right, here's another word problem based on independence. Okay, so in World War II, the odds that a British pilot were to go out on a mission, flying on whatever the mission was over Europe, that they would not return was 5%. Okay, assuming the missions are independent, what's the probability they would return from 20 missions safely? Okay, now it said each flight was independent, obviously assuming they returned. Okay, if they didn't return, then you wouldn't be talking about future events. Okay, so what we'd want to do here is say, take a complement. Right, again, this is coming from 1 minus 0.95. Excuse me, 1 minus 0.05. So if there's a 5% chance that they don't return from the mission, there's a 95% chance that they do. So what we would need here is we can just multiply that 20 times over because of the independence. Okay, we're saying that 95, on any given mission they go out, the return rate is 95%. Okay? So the odds they would return safely from 20 consecutive missions would be about 0.358. Now, we've seen this data before. Okay, I just want to show you that this formula I gave you, remember we said landline was A, cell phone is B, B given A is what we're calculating. Okay? B given A. Now you could think about it with the formula or without. The formula that I've given you, which now that I think about it, you got it on the first slide. I don't know if I showed it to you in day one. I might have. Doesn't matter. You have it now. Okay? The probability of both events over the condition. Okay? The condition is that the house has a landline. And we know that that's the case. So if I'm thinking of the table, I'm looking up here. 0.78 needs to go on the bottom. Okay? If you said event A is that they have a landline, as you can see in the formula, that is the probability of A. It's 78%. That probability needs to go on the bottom. On the top, we just need both. We have to stay within the condition of the landline, but we need to throw into the fact that they also have a cell phone. And it would be 0.6 over 0.78, 0.769. If you had the two-way table and you kind of like know how to think about conditional probability problems, you don't have to depend on the formula. The formula can be useful because it just narrows down the two probabilities that you need to identify. Here's another one from a tree diagram, same context that we saw in day one. Okay, and here's what it's asking. What is the probability here's my condition. It said good grades. So that's what I'm after. What is the probability that they are a heavy media user given that they have good grades? Because it gave us the condition of good grades. Okay? So formula-wise, I need the probability of both. That would be all the students that fit both of those events. But it should just be over, not everybody in the tree diagram, just those that fit the condition of having good grades. Now I have 6 different outcomes, so I just go through each one and say, I'll take them, they have good grades, and them, and them. So the bottom would be 0.1258 plus 0.4216 plus 0.1092. That's everybody that fits the condition. They all have good grades. We left out all the students with bad grades. Now what I need on top is specifically the students that fit both of these events. They have to come from the group that has good grades, and they have to be heavy media users. And that's them. 0.1092. We're all set up. We just have some number crunching to do. And we get 0.166. So if you know they have good grades, there's about a 16 to 17% chance they're a heavy media user. All right, this gives us a bunch of info about rates of drug use and testing. Okay? What if percent of people who test positive actually use? That's what the question is asking. What percent who test, but that's my condition, actually use? Okay, so I'm going to start my tree diagram and say I've got use. I'm just going to say, well, I don't want to say positive because or complement. I'm just going to say for this event, don't use. Because what we're calculating here is the probability that somebody uses given a positive test. Okay? That's what we're using our tree diagram to get. It says 4% are using based on this particular employer as far as individuals that they employ. If you are using, the test is 90% accurate. Right? If you're using, there's a 90% chance your test will show up positive. There's a 10% chance it'll show up negative, and there may not be enough substance in your system to catch it. If you don't use, you'd have a 5% chance of testing positive and a 95% chance that you'll test negative. Okay? So this leaves you with 4 outcomes. You can use, and test positive, use, test negative. I'm just going to say don't use, test positive, don't use, test negative. Okay? What we need are two things. The probability that somebody uses and tests positive over just the probability that somebody tests positive. Okay? So, I got a couple, I need to go through and just get the probabilities that I want. As far as the condition, I need those two groups, those two probabilities, because those represent all my positive testers, okay? Because that was the condition. 0.04 times 0.9 is 0.036. 0.96 times 0.05 is 0.048. Now, I'll have to bump down here. This is what I'm bringing down. Those two numbers together, that needs to form the bottom. And now on the top, I just need the individuals that fit both. Just the individuals that fit both, which I believe is them. They're using, and they tested positive. Crunch those numbers, and we would get 0.4287, which is an interesting probability because on one hand, the problem told us if they're using, there's a 90% chance they'll test positive. But even if we do get a positive test, there's still just a 42% chance that they're actually using. Yeah. What you would actually see in reality. I don't know, based on like the test that they're using, there are more accurate ones and less accurate ones. But on all of them, you would see that you wouldn't make any definitive conclusion from one test. If you get a positive test, the course of action is almost always that an individual gets retested. All right, because then if they test positive a second time, the odds that it was a mistake are significantly lower. But off of one, if we get a positive test, about 42% chance they're using. All right, I'm going to jump down to this last one here. Another one that's really about a complement, but it also is about independence. Okay. So 5% of these normal pregnancies will receive a positive test. Okay, about 5%. Meaning the test could show something that could indicate an abnormality, but that may not actually be the case. Is kind of what they mean. They would do a more accurate test. Okay, so if 100 women with normal pregnancies are screened or taking this test, what's the probability that you'll get at least one false positive? Well, let's think about complements. 5% of normal pregnancies will have one. Let's say we don't. Let's say the odds a woman is tested and there is no abnormality and the test doesn't show any. There's a 95% chance that will happen. Okay, which is why I took 1 minus 0.05 to get 0.95. Raise it to the 100th power. Okay? That would tell you the odds that all 100 women who, again, have normal pregnancies, that they all have the test show nothing. The test is accurate. Pregnancy is normal. Test shows that it's normal. They don't get a false positive. Okay? What we're asking when it says at least one false positive is it's saying what is the probability that the opposite of this happens. Okay, so take that probability we just took, subtract it from 1, and you'd see in a single day, if 100 women were tested, over a 99% chance one of them is going to get a false positive, meaning the test could indicate there's a possible abnormality, and then when they investigate further, they see that that's not actually the case.